In this video, I'm going to solve 4 different questions related to controlled volume analysis. I'm not going to go to the tables, though. I'm just going to refer to the tables. You're going to have to go to the tables yourself and work the tables. If you don't know how to do that, check out my previous video about problem solving using steam tables and thermodynamic tables. And if you do that, then you're going to be able to work out the tables for these problems as well. So I'm just going to go ahead and list the first question here, which tells you, so you should obviously, first of all, take out the information that is given to you, and then see if you can come up with a visualization of it. So make a diagram if you can, or make a PV diagram or a TV diagram if it's possible with the information that is given to you. So the information that you have is that you've got a tank that contains ammonia, and you've got the initial pressure and temperature given to you. And then a leak develops, so the ammonia starts flowing out of the tank at a constant mass flow rate that is given to you as well. So you've got mass flow rate that is given to you. You've got temperature, initial temperature, so we're going to call this T1. Initial pressure, we're going to call this P1. Volume of the tank, we're going to represent it by V. And mass flow rate over here, because it's flowing out of the tank, so it's going to be the exit mass flow rate. If it was flowing into the tank, it would have been the inlet mass flow rate. But because it's a leakage and it's flowing out of the tank, that's why the mass flow rate is going to be m dot E for exit. And what's it telling you is that the process is going on slowly enough that you've got a constant temperature in the tank. Okay, so it's a constant temperature process. So basically, T1 is going to be equal to T2. And what you need to find out is you need to find out the time in which half of the mass, so half of ammonia, has leaked out, and the pressure in the tank at that time. Okay, so you've got a tank, and this tank has got ammonia in it, you've got volume given to you, and then some kind of leak is developed, so you've got mass flowing out of the tank, and you've got the mass flow rate given to you as well. Okay, so if I was to try and make the PV diagram of it, I wouldn't be able to do that right now because I don't know where exactly does it lie within the dome? Does it lie outside of the dome? So if I was looking at, let's say, the PV diagram of it, and then I would have constant temperature lines over here. Okay, so I don't know if I can spot where the first state is, because I've got pressure and temperature given to me, but I need to find out whether it's a mixture, a liquid vapor mixture, whether it's a superheated vapor, whether it's a compressed liquid. So that is something that I need to do from the tables. Before I do that, I can go ahead, because we're analyzing a control volume right now. And why is it a control volume? Because mass can flow into and out of the system. Mass is flowing out of the system right now, so that's why it's a control volume. So if I apply the mass balance equation on it, which is going to be this one, basically change of mass according to time, it's going to be equal to mass flow into the system, m dot I, minus mass flowing out of the system. And because we've got no mass flowing into the system, so this is going to be 0. But obviously, we've got this happening. Mass is changing within our system with respect to time, so this is going to stay. This is going to stay as well. And this can basically, I can write this as, if I move dt onto the other side, it's going to be equal to minus m dot into dt. And now I can apply an integral on both sides, right? So I can apply an integral on both sides. It's going to be from mass of the control volume at time 0 to mass of the control volume at some time t, and we need to determine that. And over here, it's going to be again from time 0 until t. And now we can just apply this integral on both sides, and if I apply it on this side, I simplify this integral. I just have to put these limits in, and it's gonna be mass of the control volume at time t minus mass of the control volume at time 0, and that is gonna be equal to minus, because m dot e is constant, okay, it's a constant mass flow rate, so I can just move this out. And what's dt gonna be? When I simplify this integral, dt over time 0 to t, I simplify this, it's just gonna become t, and then I can plug these in, and it's gonna stay as t because this is gonna go out. So m dot e into t. Or if I substitute m dot e, exit mass flow rate here, it's going to be minus 0.04 into t. Okay, and now I can basically write this entire thing in terms of t because that is the unknown. Okay, and that's going to be mass of the control volume at time t minus mass of the control volume at time 0 divided by 0.04. Okay, I've just simplified this entire thing. You can try doing it yourself as well. And now I can work out the mass flow rates at time 0 and t. So the mass flow rate, I can work out the mass at time 0 and t. So the mass at time 0 is going to be, basically, it's our initial mass, so mass at 1. And I can find this out because I've got volume given to me, I've got initial conditions given to me at state 1. So from the relationship of specific volume and volume, mass is equal to volume by specific volume at that state. So using these two, I can go to tables for ammonia, and I can find out the value for specific volume. Okay, so I'm going to leave that as an exercise for you. How are you going to do that? I'm just going to give you a hint. It's a superheated. It's going to be in the superheated region, but you're going to have to figure out why it's in the superheated region based on the pressure and temperature information given to you. So this is going to be 0.1772 meter cube per kilogram. Okay. So now you got volume and you got specific volume as well. Just plug that in, and you're going to have your mass of the control volume at time 0, and it's going to be 2.8 kilogram, round about that. And from here, you can also now find out, you can find out the mass at the second state. And how can you do that? Because it's telling you that you need to determine the time in which half of the mass has leaked out. So that means M2 is going to be half of M1, M1 by 2. That's just going to simply be 2.8 by 2. You're going to get 1.4 kilograms. Okay, so now that you've determined these two, you can plug them into this equation over here, and you'll be able to find out the time that it takes for the mass to leak out. And that's going to be around about 35 seconds. Okay. And now that you've found out the time as well, you can go ahead and now find out the pressure in the tank at state 2. And how are you going to do that? Again, you're going to use this same concept because you know the volume and the mass at 2. So from there, what you can do is you can work out the specific volume at 2, right? It's going to be volume divided by mass at 2, and you're going to get some value from here. Let me write that down for you. 0.354 meter cube per kilogram. And now you can go ahead and look for this value in the table, in the thermodynamic tables, in the table for ammonia. And I'm just going to give you a hint again. You're going to have to go to table A15 in Shapiro's book. Okay, and over there, now you've got information given to you. You've got two different informations at state 2. You know the specific volume, and by two informations I mean information that you can use with the tables. You've got specific volume at 2, and you've got the temperature at 2. Okay, so using those two, you're going to go and interpolate in the table and find out the pressure at state 2. Okay, and that's going to be somewhere around 4.1 bar. Okay, so initially you couldn't make the PV diagram, you couldn't generate it for it, but now that you have all the information given to you, you're going to be able to identify whether the pressure has increased, whether the pressure has decreased, whether the superheated ammonia has moved into the mixture region, whether it's still superheated ammonia. So that is something that I'm going to leave up to you. You can go ahead and play with this and find out and how it looks on the PV diagram, and also go ahead and try to make the TS diagram as well. Also, one more thing that you should do is use both tables, because you've got pressure and temperature information given to you. So for ammonia, use the temperature table and the pressure table as well to find out the value for specific volume at 1. See how you're going to be able to do that. That's going to help you as well with reading the tables. Moving on though, I'm going to go to the next question now. And now you've got a case where you've got air that is entering into a 1 inlet, 1 exit control volume. And you've got information that is given to you at the inlet, at the exit, and you've been told that air is behaving as an ideal gas, and yeah, it's steady state operation. So again, we're going to start with applying the conservation of mass principle onto this control volume, and that is going to be change of mass across the control volume according to time equal to incoming. So if there were multiple inlets, let's say there were 2 inlets, then it would have been M1 plus M2. But because we've only got 1 inlet, so we only got M dot 1 or M dot I, you could say. And then you've only got 1 exit, so that is why you only write M dot 2. Otherwise, if there were 2 exits or outlets, it would have been minus M dot 2 minus M dot 3. Or minus M dot E1 minus M dot E2. Okay, so this is inlet minus outlet. And because it's at steady state, so this term goes out because there's no changes taking place according to time. Now again, try and construct a visualization of it. Okay, so you've got a control volume. You don't know what it looks like, so you can just make it however you like. But you know that it's got 1 inlet and 1 exit. So that is what I'm going to do here. Okay, you've got 1 inlet and 1 exit. At the inlet, you've got conditions given to you. 8 bars, which is P1. And you got temperature given to you, which is T1. So this is your section 1. And this is your section 2, which is the exit. And you've also got velocity given to you. Okay, so you've got velocity given to you. I'm just going to represent it by a different symbol because we used symbol V for volume. So this is what I'm using. This is why I'm using a different symbol for it. You've also got area given to you of this inlet, and this is A1. You can also write it in terms of meters square. So then it's going to be 0.002 meters square. At the exit, you've got pressure given to you, so this is P2, and you've got temperature given to you, which is T2, and the velocity given to you. This is V1, and then this is going to be V2. Okay, so you need to find out the mass flow rate, and you need to find out the exit flow area. So because this goes to 0, from here, m dot 1 is going to be equal to m dot 2, or you can just write it as m dot, because m dot 1 is equal to m dot 2, which is equal to m dot. So how are you going to find this out? From the relationship rho AV, because you already know that air is behaving as an ideal gas, so you can find out rho 1. Yeah, rho 1 area, you already have it as well, and the velocity at 1, you got that too. So, and from the ideal gas law, you can find out rho 1, which is going to be equal to P1 divided by RT1 into area, which is given to you at 1, into velocity at 1. So obviously you're going to have to convert pressure from bars into an appropriate unit. You're going to have to find out this specific gas constant, so it's going to be 8.314 divided by 28.97, okay, which is for air, and just multiply it, and you're going to be able to find out m dot from here, which is going to be around 0.36 kilogram per second. Okay. So now you've found out the mass flow rate. And now to find out the exit flow area, because you already know that m dot 1 is equal to m dot 2, so from here, what that means is that rho 1 A1 V1 is equal to rho 2 A2 and V2. Out of all of these, the only information that you don't know is area 2. So you move all the other parameters onto the other side. It's going to be rho 1 by rho 2 into V1 divided by V2 into area 1. Okay, and now rho 1 by rho 2, everything is going to get cancelled out except for pressures. Okay, so it's going to be equal to 8 by 2, pressure at 1 by pressure at 2, 8 divided by 2 into well, you're also going to have temperature as well. Yeah. So let me just write this then. That it's going to be equal to P1 divided by P2, which are pressures, and then you're going to have T2 divided by T1 into velocities, V1 divided by V2 into area 1. Yeah, okay, so R is going to get cancelled out. Obviously, you're going to still have different temperatures that are given to you, T1 and T2, so those are going to stay in here. And now this is going to be equal to 8 by 2 into 400 by 600 kelvins. And kelvins get cancelled out, and because these are ratios. And then you've got velocities, 40 divided by 350, and then you've got area, which is in centimeters square. Just leave it in centimeters square, so you're going to find out area 2 in centimeters squares as well, and that's going to be equal to around 6.1 centimeters square. Okay, so this is how you've been able to apply the conservation of mass principle for a controlled volume. And now we're going to move on to looking at a couple of examples where we not only apply the conservation of mass principle, but also apply the conservation of energy principle as well. So this is a question where you've got steam that is entering into a nozzle. You've already been told that it's operating at steady state, so the time terms, the change according to time terms are going to disappear in both the mass balance and if you were to apply the conservation of energy as well. You've got information given to you at the inlet, you've got the exit information given to you, mass flow rate that is given to you. You're neglecting heat transfer and potential energy changes, and you have to find out the exit velocity and the inlet and exit flow area. So again, because you're talking about a nozzle, you don't know what kind of nozzle it is, so I'm just going to make a nozzle, this is a CD nozzle, and obviously we don't know what kind of nozzle we're using. It could be a converging nozzle as well, but so you've got your nozzle, and now you're making the boundary of the system. Okay, so because this is something that we've discussed as well, that you can have imaginary boundaries of a system as well, where you don't really see any inlets or outlets. So over here, you've got imaginary boundaries, and you've got this as your inlet, you've got this as your outlet, and this is your basically section 1 of the flow, and this is your section 2 of the flow. At 1, you've got 30 bars of P1, you've got the temperature, which is T1, and you got the velocity, which is going to be V1. Then at the exit, you've got pressure given to you, which is P2, temperature given to you, which is T2. Okay, and you got mass flow rate that is given to you, so this is going to be m dot. So because we're talking about steady state, that means when we're looking at the mass conservation equation, obviously that term is going to go out, dm over dt, that's going to disappear, and m1 is going to be equal to m2, and then that is equal to m dot. Okay, so that's how we've got a constant mass flow rate, because m dot 1 is equal to m dot 2, which is equal to m dot, just like in the previous question. And now we can go ahead and apply the conservation of energy principle onto it, the energy balance. And I'm just going to write the full equation, and then we're going to go step by step and eliminate what we can based on the information that is given to us. Okay, so you've got work done across the control volume, and then because your mass flow rate is constant, so that's why m dot is going to be applied on the change in, let's say, enthalpy, or the change that you see for kinetic energy. So that's going to be V1 squared divided by 2, or you can just do the whole thing instead of just writing it like that. So V1 squared minus V2 squared divided by 2, plus you got the potential energy changes, which are going to be gravitational force, or like actually gravitational acceleration, sorry, into z1 minus z2. Okay, so from here you're neglecting heat transfer, that's why this is going to go out, but most importantly this is going to go out because this entire process is taking place at a steady state. Okay, and a steady state, this is what we mean. This goes out. Heat transfer goes out. You've got no potential energy changes, so you're neglecting that too. So this is going to go out. And then this is also going to go out because for a nozzle, like we've seen in one of my previous videos, and I'm going to leave the link for it over here, that for a nozzle there is no work across the control volume. Okay, so that is something that we need to be mindful of as well. And now that we've got all of this left, we can basically see the knowns and unknowns here. So you've got m dot, which you already know. Enthalpy information, H1 and H2, how are you going to find that out? You're going to go to the tables. You already have the pressure, temperature information at both the points, at both the sections. So that's why you can find out H1 and H2 from the tables. You've got velocity given to you at the inlet, so from here you can find out the exit velocity. Okay, so V2, if you simplify this, it's going to be equal to 2 into H1 minus H2 plus V1 square, and this entire thing is going to be under root. So you've got V2 that you can work out from here. Just to give you more hint about how to find out H1 and H2, you can go to table A4 because you're dealing with steam, so water. So you go to table A4, and from there you start finding out H1 and H2. Once you know those two, you can go ahead and plug them in here. You already know V1, so you're going to be able to find V2. I'm just going to give you an approximate answer so you can check your answer against it. It's going to be around 660 meters per second. Okay. And now you got this, you can go ahead and find out the inlet and exit flow areas. How are you going to do that? Because m dot is equal to area into velocity divided by specific volume. So from here, you can go ahead and use this exact same relationship for m dot 1, okay, which is going to give you area at 1 into velocity at 1 divided by specific volume at 1, and from here you can find out the area at the inlet. Okay, and you can just plug these in again. You've got to find out the specific volume from the tables, and you can go ahead and do that yourself. This is going to be around 16.6 centimeters square. Okay, area at 1, and just like this, you're going to use, hold on, you're going to use the relationship for m dot 2, and from here you're going to find out area at 2, okay, and that's going to be around 6.2 centimeters square. Okay. So you can go ahead and check these out yourself. And now we're going to move on to another problem. It's going to be a bit more complicated. So we're going up in the difficulty level from problem 1 to 2 to 3 and now 4. And that's going to be about applying both the conservation of mass and conservation of energy principle as well for a controlled volume. Okay, so you've got a turbine. Again, start off with what you know. You've got a turbine that's operating at a steady state. This is the figure for it. You've got conditions given to you at the inlet, and you've got steam that is being extracted from the turbine, and the rest is being allowed to expand separately. Okay, so you've got one inlet, you've got two outlets, then you've also got total power that is being developed by the turbine. Okay, so that's over here, power out, and that is your work done by the control volume. Okay, so this is being developed by the turbine. You're neglecting the kinetic and potential energy effects. You have to find out the mass flow rate of the steam at both the exits. You've got to find out the diameter as well. So you need to, first of all, see what you need to find out, and then go ahead and apply the conservation of mass or conservation of energy principle on it, or both. You shouldn't just start applying the conservation of mass principle onto any control volume, because you need to see, first of all, what's the information that you're being told to find out. So if you apply the mass rate balance on it, because it's operating at steady state, so the left-hand side is going to be 0, and the right-hand side is going to be, because you've only got one inlet, so m dot 1. You got two outlets, so minus all outlets, mass flow rate at all outlets, so it's going to be m dot 2 minus m dot 3, okay? And I'll just leave it at that for now, and let's call this 1, equation 1. Actually, you can also find out m dot 1 here, and the way to do that is because you need to see the information that is given to you. So m dot 1 is equal to AV1, okay, AV at 1, and this is called what? It is called the volumetric flow rate. Okay, so volumetric flow rate divided by specific volume at 1 is going to be equal to, got 85 meter cube per minute divided by, you got specific volume here that you need to find out, and you can find it out. And how do you know that? You've got temperature and pressure information given to you. So you can go ahead into the tables, and I'll give you a hint, go to table A4 and find out the specific volume at 1. So you're going to have to work with the units here as well, because this is in meter cube per minute, and then the specific volume that you're going to find out is going to be equal to some value in meter cube per kilogram. So once you find that out, plug it in, change the units for it, and I'll just tell you what V1 is so you can compare it. 6.0994 is going to be equal to 14.2 kilograms per second. Okay, so you've got M1 that you found out. M dot 2 you can't find out because you've only got velocity information. M dot 3 you can't find out as well. So because we can't find it out, we're going to have to go to the energy rate balance. And again, the left-hand side is going to be equal to 0 dE by dt. And it's going to be equal to Q dot heat transfer across the control volume minus work done across the control volume plus m dot, and now because m dot 1 is not equal to m dot 2, okay, because if you were to write this, let's say you could write it in terms of m dot 3, one of the outlets, and that's going to be m dot 1 minus m dot 2. Okay, so because you can't combine all of them and write it as m dot 1 you can't write it as m dot into the entire thing like we did in the previous question. So m dot 1 is going to have its own separate set, which is going to be h1 plus v1 square divided by 2 plus gz1. Okay, and just like that, this is for m dot 1. Just like that, actually it's going to be a minus here now because you're talking about the outlets. So m dot 2 into the entire thing, but I don't need to write the entire thing because I already know that the kinetic energy effects are being neglected, the potential energy effects are being neglected, and I can go ahead and just write minus m dot 2 into h2 minus m dot 3 into h3. Okay. What else? Because I've got no information given to me by which I can determine heat transfer rate, or it's not specified simply in some way that like how the work done is being specified, that's why I can just neglect that as well. Okay. Unless there was, let's say there were some values given here through which I could have found this out, then it wouldn't be 0. Okay, this goes to 0. And now you've got 0 is equal to minus work done across the control volume plus m dot 1 into h1 minus m dot 2 into h2 minus m dot 3 into h3. Over here, you already know what m dot 1 is, so you've got 2 unknowns here. And when you've got 2 unknowns, that is why you needed another equation. For 2 unknowns, you need 2 equations. You got one equation, which is this, and from here you can have the second equation, because you already know what m dot 1 is, into h1 minus m dot 2 into h2. And then instead of writing m dot 3, you can write it in terms of m dot 1 minus m dot 2. So just plug that in here. It's going to be minus m dot 1 into h3 plus m dot 2 into h3, right? So you just plugged in the value of m dot 3 here from this equation. Okay. Once you've done that, you can simplify it now, because on this side you've got m dot 1 h1. You can take this out, and you've got m dot 2 h2, m dot 2 h3. So from here you can simplify it even further by writing it as m dot 1 into, you can take it out as a factor, and then m dot 1 into h1 minus h3. This is 3 minus m dot 2 into h2 minus h3. Okay, this is equal to 0. So the information here for h1 and h2, you can find them out from the tables directly. Okay, just go to table A3, and you can find out h1 and h2 from table A3. But for h3, you need to be careful about it, because you've got quality already given to you, and that means that it is a mixture. So for when it comes to mixtures, then you have to apply the equation h3 is equal to hf at 3. So you find this out from the table, plus x3, which is quality, 90%, 0.90, into hfg at 3, and this is something you find from the table as well. Okay. So you find out the values for h1, h2, and h3 from the tables. You already know what m dot 1 is, you know what work done across the control volume is, so you can find out m dot 2 from here, right? So you can find out m dot 2 in terms of work done across the control volume, mass flow rate at 1 into h1 minus h3 divided by h2 minus h3, which was being multiplied by m dot 2. Okay, so you've got m dot 2 that you found out from here, and I'm just going to write down what the value is going to be so you can compare. And it's going to be around 3 kilograms per second. And then you've got to convert it into kilogram per hour, because that is what's being asked, so you can do that yourself. And from here, you can find out the value for m dot 3 as well, because now you know m dot 1 and m dot 2, and m dot 3 is going to be equal to I'm going to write this, and you can check it out for yourself. Kilogram per hour. Okay, so you're going to have to check these out yourself. And we also need to find out the diameter now. So through which the steam is being extracted, and we're extracting the steam at state 2. Okay, so we need to find out the diameter here. And to do that, we're going to do it like we saw in the previous question. We find out the area at 2, because the mass flow rate information at 2 is given to us. The specific volume is something that we can find out as well. So that is going to be V2 divided by velocity at 2. Okay, so from here you can find out the area at 2, which is going to be around 0.061 meters square. And now that you have the area, you can go ahead and find out the diameter as well, because it's a circular cross section, so that's going to be area equals pi d squared by 4, and then diameter is going to be equal to 4 into A2 divided by pi under the root. Okay, and that's going to be equal to, you can find it out yourself and check it from here, it's going to be equal to 0.28 meters. So that is how you solve different questions related to control volume analysis. Control volumes, mass can flow into and out of the system, energy changes can take place for the system, and you need to start from the very basics. You need to see, depending on what kind of question you're solving, depending on how many inlets and outlets you've got, that how you can solve that kind of question. Okay, so this is just to give you the tools to be able to solve or perform control volume analysis at steady state.